Welcome to the deep dive. Today, I want you to imagine you're sitting in the left seat. You know, the captain's seat in the flight deck of an Airbus A320.
Hmm.
You're at cruise altitude, 35,000 feet up. You're surrounded by glowing screens. There's that steady, reassuring hum of the jet engines.
It's a very comfortable environment.
Right. You're commanding this highly protected, automated marvel of modern engineering. I mean, it's a machine specifically designed to anticipate your needs, smooth out your physical inputs, and basically wrap you in invisible layers of electronic safety.
Yeah, it does a lot of the heavy lifting for you.
But then out of nowhere, you hear a sharp chime, a master caution alarm, and then another. Suddenly, the screens in front of you just light up with amber warnings.
That is the nightmare scenario right there.
Exactly.
Yeah.
So what happens to an A320 pilot when the very lifeblood of this aircraft, like its hydraulic power, starts to aggressively drain away?
What's fascinating here is that this specific scenario completely rewrites the rules of engagement for an A320 pilot.
Oh, totally.
I mean, it takes a highly automated, forward-thinking aircraft, and in the span of a few incredibly stressful seconds, it transforms it into a conventional raw machine.
Wow.
Yeah, it violently strips away the digital safety nets and forces the pilot to rely entirely on fundamental stick-and-rudder flying skills just to survive.
And that is exactly our mission for today's deep dive. We're going to use an incredibly detailed A320 masterclass as our main source today to really explore the architecture of the A320's hydraulic system.
And unpack the severe, high-stakes operational consequences for pilots when they face what the aviation world calls a dual hydraulic failure.
Right. We're looking at the system logic, the intense physical impact of these failures, and perhaps most importantly, I think, the insidious psychological traps that catch even veteran A320 pilots completely off guard during simulator training.
It really is the ultimate test. It's the moment every single A320 pilot trains for meticulously, but they obviously hope to never actually experience it with a cabin full of passengers behind them.
Okay, let's unpack this. Because to truly understand the sheer chaos of a dual hydraulic failure, we first have to understand the brilliance of the A320's normal hydraulic architecture.
Right, because it's incredibly robust when it's working.
Exactly. When everything is fine, this plane doesn't just have one main set of hydraulic vanes to move its flight controls. It has three completely independent color-coded systems: green, blue, and yellow.
That's right. And Airbus designed these three systems to draw power from diverse sources.
Okay.
So under normal, everyday flying conditions, the green and yellow systems are pressurized by engine-driven pumps.
Meaning, as long as the jet engines are turning, those two systems have immense hydraulic muscle.
Precisely. The blue system, however, operates a little differently. It relies on an electric pump that's powered by the aircraft's normal AC electrical network.
Oh, I see. So right out of the gate, you have this built-in diversity of power.
Exactly. If the engines fail, you still have electricity driving the blue system.
But the engineers didn't stop there. They added this mechanism called the power transfer unit, or the PTU. And looking at how this is designed in the source material, it's honestly a mechanical work of art.
It really is an ingenious piece of engineering. The PTU sits directly between the green and the yellow hydraulic systems.
It essentially acts as a bidirectional bridge, right?
Right. If it detects a pressure differential, meaning, say, if the green system suddenly drops in pressure while the yellow system is perfectly fine, the PTU automatically wakes up and kicks in to help out.
But here's the critical part, and I want to make sure you listen and catch this.
Right.
It transfers mechanical pressure, not actual hydraulic fluid, between the reservoirs.
Exactly. And the reason they designed it that way is absolutely crucial for survivability.
Right. I like to think of the PTU like an invisible mechanical seesaw.
I like that analogy.
If one side of the seesaw loses pressure and starts to dip, the other side physically pushes down on its end to balance the energy and keep the weak side pressurized. Yeah. And it does all of this without ever mixing the fluids of the two separate systems.
That seesaw analogy is perfect. Imagine if the green system lost pressure because of a massive fluid leak. Like, say, a piece of debris ruptured a line somewhere deep inside the wing.
Right. You wouldn't want to pump fluid from the healthy yellow system into the leaking green system.
Exactly.
Okay.
If the PTU did that, all that healthy yellow fluid would just bleed out of the exact same hole. You'd lose both systems.
Wow.
By transferring only mechanical pressure, the PTU isolates the fluid leak. It lets the green system bleed dry, but uses the yellow system's power to keep the physical mechanisms on the green side moving.
That is incredibly clever. It shares the power, but it completely quarantines the leak. And there are even more backups for emergency and ground operations, right?
Oh, absolutely. If things go really wrong in the air and you lose all your normal power, the blue system can be pressurized by something called the RAT, the ram air turbine.
I've always found the RAT fascinating. For you listening, think of it like sticking a sturdy little pinwheel out the window of your car while you're driving down the highway.
Yeah, that's a good way to picture it.
Except in this case, a small propeller drops out of the belly of the A320 into the slipstream, and the sheer physical force of a 300-mile-per-hour wind spins that little propeller so fast it generates enough physical power to keep the blue hydraulic system alive.
That's exactly how it works. And it can be deployed automatically by the computers or manually by the pilots.
And the redundancy extends to the ground too, doesn't it?
It does. When the engines are shut down at the gate, the yellow system has its own dedicated electric pump, plus a manual hand pump that the ground crew actually cranks by hand to operate the heavy cargo doors.
So Airbus clearly obsessed over making sure this aircraft always has hydraulic muscle.
They did.
Yeah.
I mean, Airbus designed the primary flight controls with incredibly deep redundancy. Every single critical flight control surface, the ailerons that roll the plane, the elevators that pitch the nose up and down, the rudder.
They're all backed up.
Yeah, they are supplied by at least 2 different hydraulic sources. Furthermore, each surface is controlled by completely independent actuators.
Right.
Because of this layered architecture, losing just one hydraulic system is a total non-event. The A320 shrugs it off entirely, the passengers wouldn't feel a thing, and the pilots simply follow a standard checklist. It's perfectly safe.
But that brilliant redundancy is exactly why a dual failure is such a massive, terrifying deal.
Exactly.
Because the aircraft is so resilient, single failures are easily managed. But losing 2 of those 3 color-coded systems completely shatters that safety net. It plunges the pilot into an entirely different, heavily degraded reality.
Yes.
Suddenly, the cascade of degradation begins.
The term cascade is exactly right. When you lose 2 hydraulic systems, you suffer a massive degradation in flight control capabilities.
Okay, explain how that works in the systems.
Well, the A320's internal flight control computers realize they no longer have the physical hydraulic muscle to guarantee the aircraft's normal safety envelopes. So they automatically revert the aircraft from its standard operating mode, known as normal law, to a degraded state called alternate law.
Let's talk about normal law first, because that is what gives the A320 its famously smooth, protected feel. When a pilot is holding the side stick in normal law, they aren't physically moving cables connected to the wings, right?
Precisely. In normal law, you aren't really flying the plane directly. You are making a request to the flight computers for a specific flight path, and the computers manipulate the hydraulic valves to give it to you.
It's like a fly-by-wire interpreter.
Yeah, and it's a highly protected environment. The aircraft will actively, physically prevent the pilot from making a dangerous maneuver.
Like what?
For instance, if you panic and pull the side stick all the way back and just hold it there, the plane will not stall and fall out of the sky.
Because the computer steps in.
Yes. The computer intervenes and limits the aircraft to its maximum safe angle of attack.
Just to clarify for the listener, angle of attack is essentially the angle at which the wing bites into the oncoming air, right?
Exactly.
Pull the nose up too high, the wing loses its grip on the air, it stops generating lift, and the plane stalls.
Right, and in normal law, the computer refuses to let the wing exceed that critical angle. It also limits how far you can roll the wings. It's like having an invisible co-pilot constantly smoothing things out.
That sounds incredibly safe.
It is, but when the hydraulics fail and the computers drop the aircraft into alternate law, those normal pitch attitude and bank angle protections are instantly lost.
Poof. The invisible co-pilot vanishes.
Gone. They're replaced by basic high and low speed stabilities, but the hard protections are away.
How do the pilots know?
The aircraft communicates this loss of protection visually. Amber crosses suddenly appear on the primary flight display, the main screen right in front of the pilot.
Yeah.
And depending on which specific 2 hydraulic systems are lost, the aircraft will also aggressively enforce a limited speed condition just to prevent structural stress on the remaining control surfaces.
Okay, I have to ask you to translate this because I want to know about the human being actually holding the controls in that moment. What does alternate law actually feel like to the A320 pilot holding the stick? Are they fighting the plane at this point?
If we connect this to the bigger picture, you have to realize how deeply an A320 pilot's muscle memory is tied to normal law.
Right.
In normal conditions, you point the nose up 10 degrees, let go of the stick, and the plane auto-trims and just holds it there.
It just stays put.
Yeah. But in alternate law, raw airmanship is suddenly required. The stick feels different. It might feel heavier or more sluggish.
Because they've lost pressure.
Right. The plane's response to the air is different because it's flying on a fraction of its hydraulic power. Those amber crosses on the display are a stark, constant visual warning that the aircraft's invisible safety barriers are gone. You have to fly it with far more intentionality, constantly making small, deliberate corrections.
And the degradation doesn't stop at the flight controls.
Right.
It hits the landing configuration, too.
Oh, absolutely.
If you lose the specific hydraulic systems that power the landing gear, dropping the wheels to land becomes a major physical chore.
Yes, the pilots must use manual gravity extension.
What do you mean?
It means it is no longer just flicking a little lever on the dashboard and waiting for a green light. They have to physically pull and turn a mechanical gravity extension handle located in the center pedestal. They have to crank it clockwise. This manually triggers a mechanical sequence under the floorboards. It hydraulically depressurizes the landing gear lines, physically unlatches the mechanical locks holding the gear up, unlatches the heavy gear doors, and then you just let gravity and aerodynamic forces rip all that heavy metal out of the belly and slam it into place.
That sounds physically exhausting, not to mention incredibly loud and jarring. You suddenly have massive metal doors catching a 200-mile-per-hour wind. The aerodynamic drag hitting the airframe must be immense.
It is a violent physical event.
But wait, I'm confused. Why isn't there just a backup electric motor to lower the landing gear? Why rely on a physical hand crank in gravity?
Because an electric motor would be useless without the hydraulic actuators to actually push the heavy metal struts against the force of the wind. Yeah, when the hydraulic fluid pressure is gone, your only remaining force strong enough to pull thousands of pounds of steel out of the fuselage is gravity itself.
That makes perfect sense, even if it sounds like going back in time 50 years. Which brings us to a really fascinating part of the dynamic, the psychological traps.
Yes.
Because dealing with heavier flight controls and manually cranking down the landing gear is physically demanding. But the true danger for these A320 pilots lies in the psychological surprises. Instructors who run the simulators see pilots fall into very specific, insidious gotchas when handling a dual hydraulic failure.
It is a classic human factors problem. The simulator exposes how our brains process or completely fail to process cascading emergencies under extreme stress.
Let's talk about the biggest trap on the ground first, before we get to the really scary one in the air. The yellow electric pump trap. This is a massive hazard for the ground crew, right?
It's incredibly dangerous.
Okay, so say an A320 has an issue at the gate, the engines are off, and a pilot decides to activate the yellow electric pump for pushback or taxi without getting explicit clearance from the mechanics outside.
Right. And turning on that pump is a deeply ingrained habit for some ground operations. But in this specific context, it's a lethal trap born purely of routine.
How so?
Well, if you activate that yellow electric pump, it rapidly pressurizes the yellow hydraulic system. But remember the PTU, that mechanical seesaw we talked about earlier.
Right, it's always watching for a pressure difference between the yellow and green systems.
Exactly. So the PTU detects that the yellow system is suddenly highly pressurized, while the green system isn't. It instantly automatically runs to pressurize the green system to balance things out.
Oh no.
Suddenly, without any warning whatsoever, the entire green hydraulic system is fully energized. If the flight controls in the cockpit aren't perfectly centered, massive metal control surfaces might suddenly sweep across the wing.
Oh man.
Heavy landing gear doors that were hanging open might violently slam shut. If there are ground personnel working near the landing gear or the wings, they can be seriously injured or killed in a fraction of a second.
That is terrifying. Just completely unexpected movement of massive heavy metal.
Yeah.
But then there is the ultimate trap in the air. It's called the direct law transition. Here is where it gets really interesting.
This is the one that gets them in the simulator.
Okay, so picture the pilots.
Yeah.
They are flying the final approach down toward the runway. They are in alternate law. They've spent the last 20 minutes mentally adjusting to the degraded handling, the sluggish stick, the lack of protections.
Right. They're managing it. They've built a new rhythm.
But the very moment they manually crank that landing gear down and the wheels lock into place, the flight control computers automatically drop a level further. The plane goes from alternate law straight into direct law.
Yes.
Auto trim is instantly lost. The FMA, which is the flight mode annunciator, basically the scoreboard at the very top of the pilot's screens, flashes an amber warning saying use manned pitch trim, use manual pitch trim. And suddenly, the aircraft handles identically to a conventional old-school airplane.
And pilots frequently fail to anticipate this sudden trim change. They end up violently fighting the stick all the way down to the flare right above the runway.
Wait, hold on. I'm putting myself in the pilot's shoes here, and I'm honestly confused. I'm already stressed out of my mind flying a degraded plane in alternate law. Why on earth would Airbus design this system to completely strip away my last remaining digital assist and drop me into direct law the exact second I lower the landing gear?
Oh, it seems wrong. Right.
It seems like a terrible time to completely change the rules of the game.
It sounds counterintuitive, but think about what a landing actually requires. To land an airliner, a pilot has to perform a maneuver called the flare.
The flare is that final nose-up maneuver right before the tires touch the tarmac, right?
Exactly. You pull the nose up to bleed off speed and gently touch the main gear down. During the flare, a pilot needs raw, unfiltered, immediate control over the pitch of the aircraft.
Okay.
If the automatic pitch trim from alternate law were still active, the computer would sense the pilot pulling the nose up and actively fight them.
Really?
Yeah. The computer would think, wait, the pilot is pitching up too high, I need to trim the nose back down to maintain speed. It would fight your inputs. By dropping the plane into direct law when the gear comes down, the computer essentially says, okay, you are seconds away from the runway. I'm stepping all the way back. You have raw, direct control of the control surfaces. Don't let me get in your way.
So the computer is actually getting out of the way for the most critical physical maneuver.
Exactly.
But the psychological impact on the pilot must be staggering.
Mm-hmm.
To put this in perspective for you listening, it feels like driving a massive modern SUV on the highway with lane assist, adaptive cruise control, and power steering, all fully engaged.
Right.
You're managing your speed, you take the exit off-ramp, and the exact second your tires cross the line onto the local road, your power steering completely cuts out and all your digital assists vanish.
Just completely gone.
The steering wheel suddenly weighs 50 pounds. You
Big-
swerve, right?
Yeah.
You'd be totally caught off guard.
That is exactly what happens in the flight deck. It is a textbook cognitive overload scenario.
Yeah.
The pilots have spent the last 30 minutes building a brand new mental model of how the plane responds to their physical inputs in alternate law. So that sudden reversion to direct law upon gear extension completely shatters that mental model right at the most high-stress phase of flight. Their brain is expecting one kind of resistance from the stick, and the airplane suddenly delivers something completely different.
That is intense.
But
But let's say they muscle through it. They navigate the cognitive traps. They wrestle the plane through direct law. They manage the flare. And they touch down safely on the runway.
which is an achievement in itself.
Definitely. But they still face one final, absolutely terrifying hurdle. Getting thousands of pounds of screaming metal moving at 150 miles per hour to actually stop.
Which is incredibly difficult without your primary hydraulic system.
Right, because the braking logic is tied directly to the hydraulics.
Hmm.
Normal, everyday braking uses the green system. Alternate braking uses the yellow system.
Hmm.
If you are dealing with a dual hydraulic failure where you've lost both green and yellow, you are completely out of pump-driven braking power. The pilot is forced to rely entirely on something called the brake accumulator.
Yes. The accumulator is essentially a highly pressurized bottle of stored hydraulic energy dedicated entirely to the brakes.
Like a reserve tank.
Right. But it is a finite resource. And when you are relying on it, the aircraft completely strips away your anti-skid protections and your auto brake protections. It's just your physical foot pressing on the pedal and the raw pressure left in that bottle.
And the margin for error here is razor thin. The accumulator only holds enough pressure for at least 7 full brake applications.
That's it.
7. There's a backup system called the Alternate Braking Control Unit, or ABCU, that automatically limits the braking pressure to 1,000 psi to try and help you conserve it.
It tries to stretch out those applications.
The pilots still have to carefully manage their physical pedal deflection to keep the pressure gauge, the ACCU press gauge, in the green sector. If you press too hard without anti-skid, you blow the tires and lose control. If you don't press hard enough, you careen off the end of the runway.
It is a delicate, terrifying balancing act.
So, what does this all mean? When I try to visualize this, it literally sounds like having exactly 7 lives or 7 pedal pumps in a video game to stop a multi-ton jet.
It really does.
But this isn't a game. How does a human pilot keep from panicking? How do they stop themselves from just slamming the brakes in absolute terror as the end of the runway rapidly approaches?
This raises an important question, and it goes straight to the heart of what Airbus defines as the golden rules for A320 pilots. Specifically, Golden Rule 1, fly, navigate, communicate.
Okay.
When a dual hydraulic failure happens, it doesn't happen quietly. It triggers a chaotic cascade of alarms. The cockpit is filled with sharp single chimes, blaring master cautions, flashing lights, and amber text filling every screen. It is sensory overload deliberately designed to grab your attention.
But grabbing your attention and actually helping you are two completely different things.
Exactly. The chorus of bells and glowing screens can easily paralyze a pilot. That is why managing the startle factor is the absolute most important skill a pilot can possess.
So they have to fight their own instincts.
Yes. Golden Rule 1 dictates that the pilot flying must intentionally ignore the blaring alarms for a moment, physically stabilize the aircraft's flight path, and mentally calm down before instructing the other pilot to even begin reading the emergency checklists.
You have to master your own adrenaline before you can master the machine.
Yes, because if you let the startle factor win, if you let the adrenaline dictate your actions, that is when you mash the brake pedals in fear on the runway. You'll blow through your 7 accumulator applications in a matter of seconds, pop the tires, and lose all braking capability.
Which is catastrophic.
Right. By aggressively prioritizing Golden Rule 1, pilots maintain the immense psychological discipline required to methodically eke out those brake applications. They have to gently squeeze the pedals, watch the pressure gauge, and carefully bring the beast to a halt.
And that ties perfectly into Golden Rule 4. Take action if things don't go as expected. The manuals remind A320 pilots to be ready for the autopilot to disconnect at any moment. They have to fly the green line on the display, manually trim the aircraft, and fundamentally remember that when that landing gear drops, they are flying a conventional raw airplane.
Yeah.
They can't rely on the computer to save them anymore.
It is the ultimate test of an aviator. Shifting from a modern systems manager mindset back to a pure stick-and-rudder pilot mindset in real time under immense physical and psychological pressure.
It really is an intense journey. Today, we've traced the harrowing path of an A320 pilot managing a dual hydraulic failure.
It's a lot to process.
It is. We started from the brilliant, invisible mechanical dance of the PTU seesaw, trying to save the systems. We moved through the scary cascade of degradation, the loss of flight protections, and dropping into alternate law.
And then the physical challenge of dropping the gear with gravity.
Right, and exploring that insidious psychological trap of transitioning into direct law right at the most critical moment of flight. And finally, that nail-biting rollout on the runway, methodically tapping out just 7 accumulator brake applications to survive.
It really makes you think about our evolving relationship with modern technology.
How so?
Well, when we build incredibly advanced, perfectly automated systems like the A320, we naturally condition human beings to rely on them.
We get complacent.
Exactly. Which leaves us with a lingering, somewhat unsettling thought. Does the very brilliance of the A320's redundancy and automation actually make it harder for pilots to mentally snap back to the raw stick-and-rudder aviation of a bygone era when that automation finally inevitably fails?
Wow. That is a fascinating question to leave you with. Next time you're sitting in the back of a modern airliner, listening to the hum of those engines, think about the complex web of hydraulic vanes and computer laws keeping you perfectly suspended in the sky.
And the intense psychological training of the human beings up front, waiting for the day it all goes quiet.
Thank you for joining us on this deep dive. Keep exploring, keep questioning, and we'll see you next time.